Okay, so today we'll really get to technical things. We're really going to prove that certain problems are NP-complete. So from Monday, we know that in order to prove that a problem is NP-complete, what we need to do is 3 steps. To prove, say, we want to prove that problem pi is NP-complete. What we need to do is first prove that pi belongs to NP, which is normally trivial. You can just say it's trivial. Normally, that will be good enough, all right? Secondly, we need to find an NP-complete problem. For the time being, again, it's trivial because so far we only have one problem. So we don't have any choice. But later on, it's become more and more difficult when we have more NP-complete problems. Finding a right problem is not easy at all. All right. And then third step is the most difficult part, to give a polynomial reduction from pi prime to our problem. Okay, so basically we need to do is the most important step actually is the third step. So basically what we need to do is find a suitable problem and reduce it to pi. All right, so today I give you quite a few examples, at least 5 examples maybe, to illustrate how we can prove that a problem is NP-complete. Some are actually not easy, I think, because it's kind of quite different from algorithms. So the problem is you may not get a feeling. Once you have feeling, and then it's become easy. The most difficult part is to get a feeling. Okay, so let me start with first reduction from set to set 5, from set to 3 set. Oh, actually, in the tutor already give you some simple reductions. So maybe some of you have, if you have taken the tutorial in the morning, then you will have some idea about reductions. So you have some feeling already. Okay, that's very important. Okay, so our first reduction will be from satisfiability to 3 set. So that will enable us to show that 3 set is NP-complete. All right. Now here, the membership in NP is obvious because the satisfiability problem is more general than 3 set. 3 set is a special case. Of course, it's trivial to be in NP because set it belongs to NP. So basically, you don't need to say anything. All right. So what we need to do is really to give a reduction from satisfiability to 3 set. 3 set is more useful than satisfiability problem because it's easier. In a sense, it's easier because each clause contains 3 literal only. Remember our philosophy when we try to identify our seed problem? We want a hard problem, but hard problem should be as easy as possible. Then it will be easier for our reduction. So in this sense, 3 set is easier. So it may be more useful when we try to prove that other problems are NP-complete. All right, so recall there's 3 sets. Each clause contains exactly 3 literals, 3 different literals. For example, we can have, so an instance of 3 sets may look like this: U1, U2, U3, and maybe U1 bar, U2 bar, U4. That's an instance of 3 sets. Yeah, suddenly realize the design of this pen actually is really technically flawed. When I touch a screen, use my finger, you see all these marks. But sometimes when the pen is not charged, I cannot even use it. You see all these dots, right? All right, so let's see how we can do it. So what we need to do actually is to use 3 sets to represent the set. So basically what we need to do is For instance of satisfiability, each clause may have one literal or two literal, three literal, so L1, L2, L3, maybe more than three literal, maybe four literals in a clause. Okay, so what we need to do is for the reduction to work, actually what we need to do is to use triples to represent a clause. That's what we mean by reduction. Actually, if our triple, a collection of triples can fully represent a clause, then it works. All right. So now let's just consider the situation. If there are only one single literal in a clause, so what we need to do is one way is to actually there are two ways to dealing with a single element clause. Maybe I'll go back to this one later. Maybe let me do either thing first. This one, of course, we don't need to change it. We just leave it there. Now, if it contains two literals, what we need to do is we need to transform this one into a clause with three literals instead of two to make it a three. All right. So in this case, actually very easy because of this equivalence. For two propositions, so this one represents P and Q. That's the meaning of a clause, PQ. All right. Now PQ is logically equivalent to 0. If I take a conjunction with 0, they're equivalent, right? So then I can write this one. It can be rewritten as P or Q, or 0 can be represented by X and X negation for some new Boolean variable X. So X is a new Boolean variable. All right. Yeah, you got it already, right? So by this one, then use distributive law. What we have, we can get P or Q or X and P or Q or X bar. So actually, this will be our solution. So a pair of literals can be represented by two triples. Then they're equivalent because they're logically equivalent in this case. All right. So what we can do is just use a new variable and do it like this. Oh, sorry. So from here, what we get is C2 can be represented by, say, L1, L2, a new variable, and here P negation. Maybe I use same order. Okay. L1, L2, P negation. So that's exactly equivalent. So now we know how to deal with two literals. So instead of single clause, now we have two clauses of triples to represent this one. All right. Okay, so that's quite easy for two. Now for one, then once we know how to extend 2 to 3, we can easily do this one. Right? So extend this one to 2, then to 3. So it will need two new variables. For example, we can do this. All right, so that will be equivalent. So we can represent a clause with single literal by these 4 triples. Of course, there are easy way to do it. Actually, if a clause contains a single literal, we can do pre-processing because we must assign L1 to be true. So that's the only way to satisfy this clause. So what we can do is assign 1 to L1. Then for any clauses contain that L1, we can delete all these clauses. That's another way to do it. So we have two different ways to deal with a clause with a single literal. All right, but anyway, it can be done. So everything is okay except when the clause contains more than 3 literals. So how can we deal with this one? All right. Okay, so let's see. So let me erase some of this to have more space. All right. Actually, using idea of induction, it's sufficient that we know how to dealing with 4 literal in a clause. All right. If we know how to do it, then we can use mathematical induction to deal with a general case. So what we do here actually is very simple. Split this one into 2. Use a new Boolean variable, say P. Then here is P negation L1, L2. So this one can be used for a clause with 4 literals. So because the law of P and the negation, so regardless of how we assign value to P, whether true or false, for these 2 parts, one of them needs to be satisfied. So that's same as one of these 4 literals needs to be satisfied. So we can easily do this. All right. Now, if it contains more than 4, we can split in this way. So for example, if it has 5 literals, oh, sorry, the last 2 should be 3 and 4. Sorry, of course. It's a typo. 3 and 4, of course. Thank you. Yeah. If there are 5 of them, all right, so what we can do, we can split like L1, L2, P. Then here is P negation, L3, L4, L5. All right. Now here the triple. Now this one, instead of 5, is 4. So by idea of mathematical induction, we can further reduce it to 2 triples. Okay. So that's how we can do it. So basically what happens is for clause with 2 literals, we extend it. And for clauses with more than 3 literals, we can replace it by a collection of triples using this idea. Okay, so we'll not spell out the whole thing. It's quite obvious using induction. All right, so from 4, if we know how to do 4, then we know how to do with 5, 6, and so on. So eventually, we can have a collection of triples to represent a set of clauses for set. So that's the actual reduction. The time it takes is obvious, linear time. All right, the time it takes. Linear is the number of total number of literals appearing in all clauses. It's obvious it's polynomial time. Usually this part will be obvious because the requirement is quite loose. We only need to be polynomial time. All right. Okay, is it clear how we can do it? All right, so you may wondering, then is it possible we can reduce to 2 sets? Use the same idea. So is it possible that we can reduce? Then it will be easier because if 2 sets is NP complete, it will be more easier to use because simpler. All right. Okay, so let's take a look whether it's possible. Of course, let me save the of course part, okay, to a few minutes later. All right, so to see whether it's possible. Because if it works, it will be very helpful for us. So let's just take of the cases, there are 3 literals, L1, L2, L3. So use the idea, we can split them into 2. So we can split them into 2 by L1, say P, L2, L3. All right, now the problem here is this one is still contains 3 literals. Does not help us. So perhaps maybe other ways, and this L1 does not look like L1. So perhaps we can do like this. Maybe L1, L2, then L2 bar, L2 negation. So somehow they need to be linked. Then new variable P, then P negation, L3. L3, okay, not L3 bar. So this one, the first one does not help. This one does not help because the second one is still 3 literals. But how about this one? Where it work? Now each contain exactly 2. All right, so I leave it to you to think about it. The conclusion is it will not work because we know that 2 sets can be solved in linear time. If it works, then we can solve satisfiability in linear time. So that will earn us at least $1 million, which is impossible because we would be able to prove that P equal NP. So this reduction certainly would not work. All right. So as this will illustrate, perhaps the one reason it would not work is because we cannot use ideal splitting to reduce the size, the number of literals in a clause. All right. So this one also will not work. Okay. Okay. So that's first reduction. So now what we have 2 problems in our tool bag. So now we know this one is NP complete. Then when we try to prove an NP complete problem, we have choices from set or 3 set. So usually, of course, we choose 3 set. So basically, it's still one problem because these two are really the same problem. One is special case of another, right? Okay. So next one is the real one. We are going to give a reduction from 3 set to vertex cover to show that vertex cover problem is NP complete. Then you will see the importance of using 3 sets instead of set because it's much easier. If we use set, it will be much more difficult. All right. Okay. So let's see. We're going to give a reduction from 3 sets to vertex cover to show that vertex cover is NP complete. All right. So first thing to note, it's obvious that vertex cover belongs to NP. So it's really trivial. So just for a set of vertices, we can easily check whether it forms a vertex cover or not, right? So vertex cover asks us to know whether it exists at most k vertices covering all edges. So that's a vertex cover problem. So if you look at satisfiability problem and vertex cover problem, they're really different, totally different problem. It's hard to imagine that we can really reduce 3 sets to vertex cover if you just look at definition of these 2 problems. Because they're really dealing with something totally different. 3 sets dealing with the satisfiability of Boolean formulas. Vertex cover dealing with vertices in a graph covering all edges. They're totally different. Okay. But however, there are very close connection between them. Let's see. It's very important in order to prove that problems are difficult, are NP complete. It's very important to understand problem. We really need to understand the problem. Perhaps from different angles, look at problem from different angles, from different point of views, then we can really understand the problem. Once we understand the problem, usually we will see connections we otherwise would not be able to see it. All right. Now look at satisfiability problem, 3 sets. What happens? We have variables. So for 3 sets, you will have variables. Say n variables. So each will get a value, either 0 or 1. All right. So you can think about a partition of these variables. So some get 1, some get 1, and some get 0. That's a choose assignment. Actually, partition these Boolean variable into two parts. One get value 1, one get value 0. So for example, U1 is get 1, U2, oh, this pen, it's all right, so that's corresponding to a Boolean choose assignment. Corresponding to this Boolean assignment, choose assignment. All right. Now look at vertex cover. We want to find at most k vertices that cover all edges. So if you look at vertices in the graph, so here are vertices in the graph. All right, say V7. Suppose k equals 3. So what happens? 3 vertices will be our solution. So these 3 vertices, maybe 2, 5, 6. So the graph may look like this if I add some edges. So the graph may look like this. All right. So these 3 vertices cover all edges. So that's what we mean by solution to vertex cover. It's these red vertices. But actually, we can regard this one as a partition of vertices. Solution is also a partition of vertices. So it's really partition vertices into two parts. This part is inside the solution, and this part is not in the solution. So see, so for choose assignment is a partition of Boolean variables. Here, vertex cover is a partition of vertices into two parts. One part is those in the solution, the other part is those that are not in the solution. All right. Now, another way to indicate it is we can, for each vertex in the solution, we give its value 1. So not in solution, we get its value 0. So now you see similarity between choose assignment and this finding a subset of vertices have certain property. So really both can be regarded as partition. And once we have partition, one part we can think about it as true, another part as false. In terms of value, one part gets 1 and another part gets 2. All right. So with this point of view, what we need to do is we try to represent an instance of 3 set by instance of vertex cover. So instance of 3 set, we have Boolean variable and a collection of clauses. Vertex cover is a graph and a number k. So we really want to have a correspondence. So use this one. Use GK to represent UC. That's what we mean by reduction, actually. And we need to construct this GK in polynomial time. All right. Okay. Now, so what's the main structure inside the 3 sets? Two things. Boolean variable. Another thing is a clause. Boolean variable consists of these individual ones. All right. So how can we represent a choose setting of these Boolean variables? So that's choose setting. How we set choose values. So that's called the choose setting. All right. So a single Boolean variable will get either value 0 or 1. How can we use a graph to indicate a particular Boolean variable gets value 1 or 0 in terms of vertex cover? So because this partition, okay, so let me use a new page. So here we have Boolean variables. I want to spend more time to explain the idea behind it. Otherwise, in 5 minutes, I can tell you the construction. I really want you to understand the idea behind it, why it works in this way. All right. So U2, U3, and so on. So how can we use a graph to represent these two sets of these variables by using a graph in terms of vertex cover? So here's the partition, maybe here V prime, here V minus V. So this one is a vertex cover with at most k vertices. All right. Now, look at this edge. Look at this edge. So this edge, we use exactly one end to cover it. So this end is covered. Let me use red. No. So use red to cover it. So the same as give its value 1 and 0 here. So we can use this very, very simple graph. In this case, just an edge to represent two setting. So if we use this one to represent Boolean variable U1, so we can use this very simple graph to represent two setting of this particular Boolean variable. Depends on which end is used in the vertex cover. So with this idea, what we can have is we can construct the graph in this way. For each Boolean variable, and now we haven't touched the number of clauses yet. We're talking about choose setting first. How can we represent the choose setting by graph? We'll get to that one later, okay? Now what happens is for each Boolean variable, you choose vertices to represent this one. So one side, one end is we use UI, another end use its negation. So each will have this. Oh, so this one is the U3. So this one. Okay, so that's what happens. So each Boolean variable will be represented an edge. So we have m disjoint edges, n disjoint edges. So it's up to un. So here we have n disjoint edges. All right, now the correspondence is in this graph, we consider vertex cover of size exactly k. Exact n, sorry, here's n, okay. Consider vertex cover of size n. Because each edge we need one. Actually, at least at most n means exactly n. Because these edges are disjoint, we need one for each edge, right? So that's what means is for each edge, we choose exactly one end in the vertex cover. Maybe this one, this one, this one, and this one, and so on. That's exactly corresponding to a choose assignment on the left side. So if this part is 1, this part is 0, so it's corresponding to choose assignment 1, 1, 0, 1. All right, so we solve the first problem. We know how to do choose setting of Boolean variables by using vertex cover in a graph. So the graph is very simple. All right, so these are called the choose setting component. So this one is called the choose setting component. Because the function is to set choose for these Boolean variables. So each edge is a choose setting component. So we have n choose setting components. All right. So we resolved one issue. We now know how to represent choose setting of each Boolean variable by an edge in this very simple way. Now another important part is satisfaction of a clause. So let's say it's L1, L2, L3. So another important structure in an instance of 3 set is a clause, it's a triple. So how do we know it's satisfied? So this one is satisfied if at least one literal is true. So how can we use vertex cover to represent this fact? So intuitively, from the what we just have done for choose setting, so intuitive perhaps we will have three verses intuitively. So it's very natural because these are three objects. So perhaps we'll have this in the graph. So each is object in a graph. So typically will be a vertex. We're not quite sure, but it will look like something like this. How can we construct a graph so that this graph will enable us to tell whether this clause is satisfied? So in other words, we can check the satisfaction of a clause by a graph, or test the satisfaction of this clause. How can we do it? All right. So certainly we need to have some edges. If without edge, nothing happens, right? Because vertex cover dealing with vertices covering edges. So what happens is perhaps we link them into very natural way. So a triangle. You make a triangle. It's very natural, right? Since there are edges. So now let's see what happens. Now in a triangle, how many vertices do we need to cover all three edges? In a triangle, two edges, right? Now, for a clause with three elements, it's symmetric. So triangle is symmetric. So basically it needs to be symmetric. So that works perfect good. But how can we use triangle to tell whether this clause is satisfied? It seems not able to. So suppose we choose these two, or we choose these two. What's the difference between them? Actually, we cannot tell, right? If just a triangle. Whether it's true or false, because eventually true or false will be represented by a graph. So some information will be obtained from this true setting components. So for this reason, we must have a connection with outside. So this is within a clause. Now we must have some communication between this one and true setting. All right. So that means there must be some edges connecting this part to outside. So there will be edges for this part connecting to outside. So something. Now look at this one. How many verses do we need to cover this graph? Cover all edges of this graph. So originally a triangle just two. Now we need three, right? Because of these leaves, we need three. So in order to cover all edges, what happens? Cover this one, so that will cover these two. Use this one, cover this one, and this one. Use this one, cover this one, and this one. All right. So this one does not seem to help us because in order to cover whole thing, we need three edges. Three verses. All right. Now look at the following situation. All right. Now suppose one outgoing edge is covered by vertex outside. So suppose this edge is covered by this vertex. Now how many vertices do we need to cover all edges in the remaining graph? Two, right? It's quite obvious. We can use these two. Now do you see the construction? Actually, it's not that difficult now. Once you see this, so what happens is if this one is 1, all right, so that means if this one is same as this one, so this L2 here, if this one is same as this one, it's also L2. So that means this one is true literal. All right, so that means this clause contains a true literal. In this case, we only need 2. All right. So once you see that, then the construction naturally pops out, the final construction. So we have two static components, and then we'll use this one for satisfaction testing. So that's the satisfaction testing components. So eventually it's a collection of them, so will be S here. All right. So here we can use a triangle as set to test the satisfiability of this clause. All right. Now we are going to combine them together. All right. So let's see. Previous. Let me check if. Okay, this one may be okay. All right. So we have two settings here. Let's just use this part. So erase this part. Okay. So let's see. So suppose we have a U1, U2, U3. All right. So this clause, this triple. So what we do is use U1, U2, U3. I use same name, but actually they're different verses. All right. So perhaps let me maybe I should. Otherwise, you may get confused. Maybe U1 put a star here. Okay. So U2, I put a star here. U3 also put a star here. So that corresponds to U1, U2, U3. All right. All right. So what happens is just link U1 star to U1, U2 star to U2, U3 star to U3. All right. And similarly, if I will have another literal, and so another clause, say U1 bar, U2 bar, U4, then we have U1 bar. Again, actually need to be careful. Here the name actually should be different because sometimes contains same literal. In this case, let me see. Maybe. All right, now this U1 bar, see two actually different verses. All right, so typically if I use a clause, maybe so then if this one is CI, maybe that's C3, the third clause, then I maybe put a subscript here, that's C3. Okay, so here if C5, then I would put C5 here. So to indicate that different variable, different verses. All right, so for simplicity, I use same name. All right. So, but meaning actually they're different ones. Okay. So with this understanding, actually they're different ones. So now the connection again is very simple. U1 star, sorry. To U1 star, U2 bar to this one, U4 to somewhere here. Or maybe I make it UN instead of this one. So instead of this one, I say UN. So this one goes here. That's the construction of the graph. That's our graph G. All right. Now we need to set value of k. What is value k? For each Boolean variable, there are exact one vertex. So it's n here. So this part is only n verses, one each. For this part, two each. For each triangle, we use two. So it will be n plus 2m. M is the number of clauses. All right. So from instance of 3 set, you see we construct an instance of vertex K cover. So K, where K equals N plus 2M. All right. Our previous discussion actually ensures that UC is satisfiable if only if G contains a K vertex cover. So actually the construction led by the correctness. We already in our discussion, it's already implied that the construction works. All right. Of course, we need to prove it formally, and it's in the notes. I don't think we have time to go over the proof formally. All right. Okay. Any question about that? Now, do you understand how reduction works for 3 sets to vertex cover? It's very important. As I said, it will be in the final exam. Also, in the homework, I asked you to mimic this reduction from 4 set to vertex cover, but a special kind of vertex cover, where we require this part to be connected. This one is connected. All right. So in the homework, I ask you to do this, mimic this reduction. Also, that will help you for the final exam, because I said again, this one, homework form already posted. It's already posted. I posted it yesterday. All right. So that exercise will help you to really understand the reduction. All right. Okay. Is that clear? Any question about this reduction? Because it's extremely important. You can forget anything about NP completeness, but you must remember this reduction, how it works. Of course, in the final exam, it may be not just straightforward, give you like these two things, ask you to construct this graph. That's trivial, right? It will be more than this one, of course. But if you fully understand that, you can work out. If I change the problem a little bit, you'll be able to work out the thing by yourself. So what I really mean is you will be able to reproduce this proof by yourself, and you understand the reason behind it. Only at that time you can say you fully understand the reduction. Not just try to remember this reduction, but you need to understand why it works in this way. All right. Yeah, K equal N plus 2M is, for this part, we use one vertex in the vertex cover for each Boolean variable. So that's N. For this part, for satisfaction testing component part, we have M clauses, each use 2 vertices. Each triangle use 2 vertices. All right, so that's where we come up with this number, N plus 2M. All right. Okay. All right, I think time is up. Yet, let me say one thing about what a 2N part is the satisfaction part. We have M clauses here, M triangles. Each triangle we use 2 vertices in the vertex cover. So it's 2 times M. Okay. All right. In the homework, for reading, I put a note there for reading chapter 6. Then after that, I said not recommended. Actually, I don't really recommend you to read that part. You get confused, actually. That textbook does not use decision problems. They rather use what they defined search problem. It's different from what we mean by search problem. The way they dealing with that is not very good at all, I think. It's not good. All right. So I really don't recommend that one. The one I recommend is the MIT book. You can find online version. If you really want to understand more, you can read that chapter, the NP completeness chapter in that book. It's of course, it's maybe a little bit more difficult to read that one. It's more technical, maybe. All right. Otherwise, I think the lecture notes will be good enough. Plus, of course, my lectures should be good enough to explain the ideas behind the theory of NP completeness, as well as the technical part. The textbook actually for this part is quite lousy. It's not good at all. I don't like it at all. It's not good. Technically, it may not be that sound, and it's not explaining very well. Okay. Also, one minor thing is a Hamiltonian cycle. No one knows Ludrata cycle. No one uses that name. So all people, I think, know the Hamiltonian cycle. Okay. No, G is whole graph. G is the whole graph. Whole graph is G. G is this part. Whole graph is G. All the edges, all the vertices. All right. Okay, I think time up, and we'll continue Monday on with more reductions. All right. Okay. As I said, the final exam will cover up to NP completeness. So I will discuss a little bit on approximation algorithm and FPT algorithm to give you a taste, but these will not be covered in the final exam. All right. Okay. So see you on Monday. Bye-bye. Any questions? Okay, in the tutorial, tutor will give you a few simple reductions. I think it will be very useful. So these reductions seem to be very simple, but it's not trivial to come up with these reductions. So I believe you must see at least 20 or 30 different reductions in order to have a feeling of NP completeness proofs. All right. Okay. Okay. See you next week. A homework form is up there already, so you can start enjoying it by thinking about it at least. Okay. Bye bye.